Hello, welcome to the Edsim++ instruction video called Effects. My name is Nico Punt and I will show you today the available effect objects in the Edsim++ PKPD library. In Edsim we discriminate between several types of effects, and the major discrimination is the physiological effects and the bacterial killing effects. And let me start with the physiological effects. Here we have two types of submodels. The first type are the so-called direct response models, where there is a direct relationship between the concentration of the drug and the effect of the drug. And what you see here is the equation for the classical Emax model, and we call that sigmoid in Edsim. And the other type of model are so-called indirect response models. And here the effect is part of a differential equation. And but you see this Emax model coming back again, but it's, as I said, it's part of a differential equation. Okay, so let's start experimenting with these objects. And what I will do is I will not directly combine the pharmacodynamics with pharmacokinetics. I will try to first isolate the pharmacodynamics. So what I will do is I add a compartment, and in this compartment I want to add different doses of drug. And I could use an injection object for this if I add an injection like this, and I make the connection. What I could do is I say, okay, I want to construct a log dose response. So what I could say, okay, I give 1 milligram here at 0 hours, and then I want to go 1 decade higher, so I have to add 9 milligrams right here, so I have a total of 10. So if I want to move up to 100, I would add 90, so I have a total of 100. And if I want to go to 1000, I would have to add 900. Of course, this must be 1, 2, and 3 hours. Okay, but this is a bit, well, this is not working, obviously, especially if you want to take half-decade steps and so on. So this is not that convenient. So we have an alternative. We have a special object, which is very useful when you want to isolate the pharmacodynamics, and that's the T-log dose input object. And if I double-click here, you can see that this object has two options. First a mode, and the second option is a transform. And the mode has two values, replace or add. Replace means that it simply will replace the existing amount in the target compartment, while add obviously means that you add the dose to the already present amount. We will use the replace because it's more convenient. When compared, for instance, to the injection object we used earlier, which added the dose. And the second option is transform. It has two values. First, log or linear. And log means that the dose you enter is interpreted as a log dose value, which is also easier when you want to construct log dose response curves. Okay, now I can now enter here a schedule. And remember, so the value I'm going to enter here is interpreted as a log dose. So I can simply enter here, for instance, -3, which then essentially means 0.001 milligrams. And because I use a standard compartment with a default volume of distribution, and that's of 1 liter, this will be equivalent to 0.001 milligrams per liter. Okay, so the next step I'm going to take is half a decade, so is -2.5. And I can do a little trick, which you of course probably know from Excel. I can now extend this range, so I have covered the range from -3 to 5. And I must assign a time to this dose. So the first will be 1, the first will be 0, the second will be 1. And I can do the same trick of extending this range. Alright, so I can now have a look by simulating this. And you see here those doses building up. in a logarithmic fashion. I can demonstrate that by switching on the log scale on the y-axis. See, now it's linear. I will switch it off again. Okay, so now it's time to add our effects object. So I add here an effect object, and it defaults to the classical Emacs model, sigmoid. I'll make the connection. So I double click it and go to the variables section, and I click here on observed. I want to observe the effect. And what I do not want to observe right now, if I click here on this compartment, is the concentration. Now if I simulate this, you see here the effect over time. But what I want to have is, of course, concentration versus effect. So I can change that right here. I can say here, I want to have this concentration as the x variable. Now if I simulate this again, you get this classical, what I would call saturation curve. So the last step we have to take is select a logarithmic scale on the x-axis. Now simulate this. And here we are with a typical log dose response curve. What I can also do is, if I want to see the curve right here, I can activate the mini charts, so we see the curve here again. And now we're going to play a little bit with the parameters of the Emacs model. And it would be nice if we can have both models simultaneously, so that we can make a comparison. So I simply duplicate this model. And we're now going to play with the parameters of this effect object. And one of the first things we can change, of course, we can change the EC50 value. We will change it from 50 milligrams per liter to 5. So a factor of 10 lower. And if I simulate this again, you see this shifting to the left. And if I look here, you see both curves. And I'll make it a little bit easier by switching on the grid lines. So both the X and Y grid lines will be switched on. So you can see here with the blue curve, we have an EC50 of 50 milligrams per liter, and now with the second one we went down to 5 milligrams per liter. So let me restore this EC50 value to 50, and let's change the Emacs value, for instance, to 75. Simulate it again, and we see now here we brought down the Emacs value. Let's set it back to 100 again. And now let's move up the effects E0, so the initial effect without any drug, and then we get this type of profile. So move it back again to 0, and the last parameter here in our classical Emacs model is the hill coefficient, which is a measure for the steepness of the curve. So I will change it from 1 to 2. Simulate it again, and you see the curve gets more steep. So this is a very nice way of investigating and playing around with the Emacs model. So now it's time to combine effects and pharmacokinetics. So we're going to do some real PKPD modeling. So I will start with a simple compartment model. I will add an input, I'm adding an output, and we have this a little bit more to the center. And if I simulate this, we get a nice curve. Now what I can do is I can add an effect object right to the central compartment. If I say I want to observe effects, and I can simulate this, you see here the effect values. If I look here, you can see it as well. Please note that here the effect and the concentration share the same axis, It could be more convenient to have the effect have its own axis, and you can do that quite easily by switching here the axis checkbox on the effect and simulate it again. So if I look here, you see here now that the effect has its own axis on the right. Okay, but hooking up an effect to the central compartment is not very common, and because effects, of course, usually take place in some peripheral compartment. So what I will do is I will delete this effect object, and I will make a two-compartment system. I'll make the connection here, and now I will hook up the effect object to this peripheral compartment. I must say I want to observe the effects, and I will again connect it to the right axis, and we'll do a simulation again. So here you see the intravenous profile in the central compartment, and here you see the profile in the peripheral compartment, and here the associated effect in the peripheral compartment. Now what is a bit of a problem is that you then have to switch to a two-compartment system, and it might very well be that this effect compartment is so small that it has no real effect on the central compartment, so that you don't actually see the two compartment kinetics. So what you can do then is use a so-called virtual compartment. So if I delete these objects, and I will add another compartment here, and I will change its type from peripheral to virtual linked. I will make the connection, and I will connect an effect object to this virtual compartment. And again, I want to observe the effects. I want to have the right axis, and if I simulate this, I want to observe the concentration in the effect compartment as well, right there, and here are the results. So the nice thing of a virtual compartment is that it does not participate in the mass balance to the compartments to which it is connected. So from a pharmacokinetic point of view, this is still a one-compartment system. But yet you are able to simulate the concentration, only concentration, in a peripheral compartment and attach an effect model to it. So in fact what we are dealing here with is the classical Shiner link model, in which this virtual compartment is so-called effect compartment. Okay, so what I finally want to show you with this model is the correlation between the concentration and the effect. So what I can do is, if I double click on some of the objects and go here, I say, okay, I want to correlate the concentration in the central compartment with the effects right there. Now, and if I simulate this, you get this kind of curve, and this is what we call a hysteresis curve. Because of because the effect is correlated to the concentration in a peripheral compartment, in a virtual compartment, effect and concentration are more or less out of sync. So what we have to do is we have to correlate, of course, the effect to the concentration in the virtual compartment, in the effect compartment. So here C2, and if I simulate this, you get this nice curve. And the only thing I have to do now is set the log scale on the x-axis, and then we get this partial log dose response curve. But now we extracted it from a real PKPD model. So I will continue now with the indirect response model. All these indirect response models have the same basic scheme, which means that there is some kind of precursor which is produced, And this precursor is transformed into a what we call response variable. So into an entity that has direct relationship with the response. And this entity, of course, is also removed again. And a drug may act on any of these three steps. I've taken this picture from a very nice review article from Sharma and Yusko. And an example of this is, for instance, the effect of ibuprofen on body temperature. And so it's believed to act as follows: that you start with arachidonic acid, which is then transformed under the influence of the cyclooxygenase enzyme to prostaglandin E2, which will have an effect on body temperature in the hypothalamus. And ibuprofen inhibits this enzyme. Okay, so let's try to make a model. And I will start with a compartment, and we add an input to it, and we again will use this log dose response input, because we have so much control in what's coming into this compartment. And I will use the linear mode to make it a little bit easier. So, and what I do is I add a dose here, and I will remove these ones, and I will add, say, okay, I will add 20 milligrams at 10 hours, and I will simply remove these 20 milligrams after 20 hours. So if I simulate this, I get this kind of response. 10 hours, that's 20 milligrams. After 20 hours, it's gone again. So this is a very nice experiment to control the concentration. Now I'll add a direct response, so the classical Emacs model, to this compartment, and I will set some of the parameters. So my initial effect without any drug, I'll set to 37, being the body temperature. EC50, let's say it's 20 of this drug, and the maximum effect is, well, let's say a hypothetical 20 degrees Celsius, and the Hill coefficient will be 1. I have to say I want to observe the effect. Okay, and let's see what the results are. And here you see then the direct response. And if I look here, so here, drug, removed again, and you see a direct relationship with the effect. Okay, now I will duplicate this model. And I will change this with the indirect response model. And let's set the parameters. So I want to observe this again. And with the parameters, okay, we have to re-enter them. So initial effect 37 degrees Celsius, EC50 20 milligrams per liter, maximum effect 20 degrees Celsius, and these two are the rate constants for the formation here and the removal of the effect variable, response variable. And we set them initially to 0.5. Okay, and we do a simulation. Now let's have a more close look here. So here you see that, in spite of the fact we have the same impulse in dose, it takes time for the effect to set in. So here you have a effect from 37 to, in this case, 28 degrees Celsius. And in the moment the drug is removed again, it also takes some time to let the effect wear off again. So this is the typical characteristic of the indirect response models. So we can play a little bit with the parameters again, of course. So I make a copy of the whole model. Put it here. I'll double click here and say, okay, let's say that the synthesis rate and the right here and the removal rate are twice as high. Simple as that. Do a simulation and let's look at the results. So you can see it here. So this was the original curve, and now we increase the synthesis and removal rates, and you see the effect of this. So now I will continue with the last group of effect models, being the bacterial killing models. And all differential equations in the bacterial killing models have the same kind of template. There is a bacterial growth rate and a bacterial killing rate part in the differential equations. And we have three types of models in the library at this moment. We have a static model where there is no adaptation of the bacterial population to the drug. We have an adaptive model where you see some kind of adaptation over time, as indicated by this alpha parameter. And we have another different type of model, which is using the MIC. So here the MIC are actual part of the equations. Okay, I already prepared a model for this demonstration. I'll pick it up here. So it's a simple one compartment model, and in this compartment I give a series of injections. So here is a dose of 10 milligrams, and it's with an interval time of 8 hours, so 3 times a day, and I give 5 dosages. And what I'm going to demonstrate is the adaptive kill model, T-kill adaptive. Okay, so let's do this simulation. And let's have a look at the results. So what you see here is the concentration of the antibiotic drug. And what you see here in red is the population of bacteria. So at high concentrations, you see that the bacterial killing rate is higher than the bacterial growth rate. And you see that the population size decreases. But in the moment the concentration of the drug is below a certain level, you see that there will be regrowth of the population until we give the next dose. And this repeats itself for each dose. What you see also is the adaptation phenomenon. So over time the killing is less and less effective. So you see as a net effect more regrowth. So it's very interesting with this type of models to for instance study the effect of different routes and different ways of administration. So what I could do, for instance, is I change this injection to an infusion. And I say, okay, I will then administer this dose over a certain period. For instance, 1 hour. And let's see what happens then. If I simulate this, if you watch closely, you see already there is somewhat less regrowth. So I can increase the infusion time. So I give the same dose, but simply over a longer period of time. And let's see what happens. So here I selected a 2-hour infusion. You see there's even less regrowth. So we could go to, let's say, 3 hours. And you see it's more effective than these injections. So these type of models are very suitable to study different therapeutic regimes. So this concludes the video on effects.